Dobro. History. Archive.
December 26, 2004. For many people, particularly in the Western world, it was Boxing Day, a quiet holiday, maybe some post-Christmas sales, or a day at the beach.
Just a day to wind down after the festive week. But that quiet was, shattered.
Shattered is the word. In the Indian Ocean basin, that holiday was transformed into a planetary trauma, an event that would fundamentally alter not just lives, but global aid, ocean monitoring, and quite literally the physical geometry of the Earth itself.
We are, of course, talking about the Sumatra-Andaman megathrust earthquake and the devastating tsunami that followed. The scale of the human loss is, even now, just difficult to comprehend.
What were the final numbers?
The best estimate is around 227,898 lives lost across 14 nations. And what's critical to understand is the reach of this. It wasn't just the shores of Indonesia. The destruction stretched all the way to the east coast of Africa.
Thousands of kilometers away, Somalia, Tanzania.
Exactly, countries that had no idea what was coming.
And we have to emphasize right at the top that the victims weren't just from that region. Because it was peak holiday season, the casualty list was tragically international.
It really was. This wasn't a localized disaster. It was a shared global shock. Citizens from over 50 nations were lost.
The numbers are just heartbreaking. Over 500 people each from Sweden and Germany. Mostly tourists, right?
Mostly tourists, yes. Families on vacation on the beaches of Thailand and Sri Lanka. I think that's why the entire world suddenly woke up to the power lurking beneath what was, considered a relatively quiet ocean basin.
It made it impossible to look away.
Completely.
So our mission today is to take a deep dive into this event. We're going to unpack the terrifying physics of it all, from the seismic rupture that unzipped 1,300 kilometers of seabed and actually shifted the Earth's axis,
to the hydrodynamics of that infamous black water. And then we'll trace the evolution that followed. The 2 decades that took us from a total vacuum and warning systems to the AI-driven tech we have today.
The initial shock factor alone is overwhelming. This wasn't just a big earthquake.
Not at all. Looking at the pure metrics, it was the 3rd largest seismic event ever recorded by modern instruments. The energy release was just staggering.
Okay, let's unpack that. Let's start right at the source, the precise mechanism that allowed the Earth's crust to tear apart for 8 solid minutes.
Right. So the event originated in the Sunda Trench, just off the western coast of Sumatra. This spot is one of the planet's most active geological laboratories. It's a convergent plate boundary.
Meaning 2 plates are colliding.
Exactly. The oceanic Indo-Australian plate is aggressively subducting or diving underneath the continental Eurasian plate, or more specifically what's called the Burma microplate.
And for centuries, these 2 colossal pieces of crust had been locked together.
Locked tight by friction. You can picture it like a massive compressed spring just accumulating strain year after year, century after century. The upper plate, the Burma plate, is being dragged down and deformed.
Build up all that tension.
An incredible amount of elastic strain. And then at 0.58.53 UTC on December 26th, that frictional lock finally broke. The overriding plate snapped back upward and seaward with incredible violence.
And that sudden movement is what displaced the column of water above it.
That's the moment the tsunami was born.
We've had major earthquakes before, even in that region. What made this one so fundamentally different, so catastrophic?
It comes down to one thing, really. The unprecedented scale of the rupture length.
The length of the tear in the crust.
Precisely. A very large subduction zone earthquake, maybe a magnitude 8, might rupture a fault segment of, say, 100 to 200 kilometers. This fault, though, it unzipped northward from the epicenter off Sumatra.
How far?
A staggering 1,200 to 1,300 kilometers, all the way towards the Andaman and Nicobar Islands.
Wow.
To put that in perspective, that's like a zipper tearing open the Earth's crust for a distance equivalent to the entire length of California.
A 1,300-kilometer rupture. So that's the key variable that turned a regional disaster into a transoceanic one.
It's the primary determinant, yes. Because the rupture was so long, a huge section of the seabed vaulted upward, displacing a colossal volume of water over an enormous linear distance. That's what gave the wave the energy to cross the entire Indian Ocean.
And if it had been shorter?
Had the rupture been, say, 200 kilometers, the energy would have been localized. Devastating for Indonesia, certainly, but it would have dissipated quickly. It wouldn't have reached Africa with destructive force.
And the duration of this.
Yeah.
It's another thing that's hard to grasp. Earthquakes usually last for seconds. This one went on for 8 to 10 minutes.
That sustained duration between 500 and 600 seconds of the crust continuously tearing is a sign of just how complex the rupture was. It was propagating at about 2.8 kilometers per second.
And this long, sustained movement, this slow slip, that's what confused the initial readings, right?
Absolutely. The first seismic readings, which focus on the short period waves that arrived quickly, severely underestimated the energy. They came in around magnitude 8.0, maybe 8.5.
Which is big, but not.
Not a 9.1. It wasn't until scientists analyzed the long-period seismic waves, the ones that account for that massive, slow movement over the entire 1,300 kilometers, that they corrected the moment magnitude up to that 9.1 to 9.3 range.
And that discrepancy is crucial for understanding the warning failures.
It's everything. If officials had only gone on that initial 8.5 reading, they would have completely misjudged the basin-wide danger.
So if we pull back from the fault line and look at the planet as a whole, the energy release was equivalent to what? Something like 23,000 Hiroshima-type bombs?
That's the estimate, yes. And that level of geological violence does things to the very architecture of our planet.
It changed time and space.
Effectively, yes. The scale of the mass redistribution was immense. When the heavy Indian plate dove deeper and the lighter plate snapped up, it changed how the Earth's mass is distributed relative to its core.
Which, according to NASA geophysicists, meant the planet literally spun faster.
Correct. It's the principle of angular momentum conservation. Think of a figure skater pulling their arms in to spin faster. By moving a colossal amount of mass closer to the rotational axis, the Earth sped up.
By how much?
The net effect was a shortening of the day by somewhere between 2.68 and 6.8 microseconds.
That is just mind-blowing, the sheer power of it, to actually speed up the planet even by a tiny measurable amount.
It is measurable.
How do you even measure a change that small? It's less than a millionth of a second.
They use incredibly precise techniques, like very long baseline interferometry and satellite laser ranging. They track the position of things like quasars and satellites with such precision that even a minute change in the Earth's rotational rate becomes discernible over time.
So it wasn't just the speed, it also shifted our axis.
That's right. The event physically shifted the Earth's mean north pole, the rotational axis the planet balances on, by about 2.5 centimeters, about an inch.
The planet wobbled and settled into a new spin.
In essence, yes. And to top it off, it even made the Earth fractionally more spherical. It decreased the planet's oblateness, that slight bulge at the equator, by 1 part in 10 billion.
We really have to stop thinking of this as just a disaster and see it as a fundamental geophysical event.
It permanently altered the planet's architecture.
Okay, let's transition from the rupture itself to the water. Microdynamics of destruction. How did that displaced water become a killer wave that crossed an entire ocean?
Right. So once the seabed heaved and displaced those trillions of tons of water, a series of waves radiated out. And the way they travel across the deep ocean is one of the most counterintuitive things about tsunamis.
Because even though the ocean is, 4 kilometers deep on average, the tsunami acts as a shallow water wave.
Exactly. And the reason is scale. A tsunami's wavelength, the distance from crest to crest, can be over 100 kilometers long. Since that's so much larger than the ocean's depth, the wave is constantly feeling the drag of the seafloor, even 4,000 meters down.
And that dictates its speed. There's a simple equation for it, right?
A remarkably simple one. Velocity equals the square root of gravity times depth. So V equals the square root of G times D.
So you plug in the numbers for the deep Indian Ocean.
And you get a phenomenal speed. Those waves were traveling between 500 and 1,000 kilometers per hour. That is, for all intents and purposes, the speed of a jet airliner.
A wave moving at the speed of a plane. That's the definition of the stealth wave.
Absolutely. Because at those speeds, out in the deep, the wave's amplitude was less than a meter, maybe just a few dozen centimeters. If you were on a container ship out there, you'd feel nothing more than a long, gentle, maybe unusual swell.
The entire catastrophe was literally passing underneath them, completely unnoticed.
There was no way for ships to radio a warning, nothing to see.
Which explains how it could cross the ocean so fast. Sri Lanka in 2 hours, Africa in 7. But if it's only a meter high, how does it become a 30-meter wall of death when it hits the coast?
That is the critical process of shoaling. As the wave train leaves the deep ocean and hits the continental shelf, the shallow water near the coast, the depth, D, decreases drastically.
So the equation changes.
It has to. To conserve its energy, the wave has to respond. The velocity drops sharply because the depth is lower. And to compensate for that loss of speed, the amplitude, the height has to increase dramatically. The wave is forced to slow down and stand up.
A massive transfer of energy from speed to height.
And the effects were devastating. Near the epicenter in Banda Aceh, run-ups were between 15 and 30 meters. In some areas, localized geography funneled the water to heights of 51 meters.
And it just kept going inland.
Up to 3 kilometers in some places, scouring the landscape completely clean.
Before that wall of water arrived, though, there was the other defining image of this disaster. The deadly precursor. The ocean pulling back.
The leading depression. Because of the way the fault ruptured, the initial movement of the seabed facing east toward Thailand was downward. This created a massive vacuum effect.
It literally sucked the water away from the shoreline.
For hundreds of meters, exposing reefs, fish, and sand that no one had ever seen before.
And this created the ultimate curiosity trap.
It did. The Indian Ocean hadn't seen a major tsunami in living memory, so people, especially tourists, didn't recognize it as a profound warning sign. They saw it as a natural wonder.
A bizarre, once-in-a-lifetime event.
Exactly. Survivor counts from places like 𝐃𝐄𝐄𝐏 are just chilling. They describe people walking out onto the exposed seabed to collect fish. There's one story of a woman trying to throw stranded fish back into the water, a humanitarian impulse that cost so many people their lives when the crest arrived just moments later.
And the arrival of that wave.
Yeah.
What did it look and sound like?
Survivors consistently reported a sound, a deep rumbling hiss, or a fizzing or frothing sound.
Like a carbonated drink.
Like a massive one, yes.
Yeah.
It's the sound of air being trapped and churned in the turbulent leading edge of that enormous mass of water.
And the water itself. It wasn't blue.
No. Universally, survivors called it a black wall or black water. This was due to extreme turbidity. The wave's momentum just ripped up everything in its path. Seabed sediment, soil, mangrove swamps, sewage, oil from storage tanks.
So it wasn't water anymore, it was a slurry.
A dense, toxic slurry. And that's a vital detail because that density and viscosity give it far greater destructive momentum. It didn't just flow around buildings, it struck and pulverized reinforced concrete. It stripped vegetation down to the bedrock.
Let's look at that regional impact then, because it differed so much depending on geography and warning time.
It really did.
We have to start in Indonesia, Banda Aceh, the epicenter. They had less than 20 minutes warning time and suffered the greatest loss of life.
Approximately 167,736 victims. The city was virtually erased. And yet, amidst that flattened landscape, one structure famously remained standing, the Baturaman Grand Mosque.
It became a refuge, a beacon.
And for the local population, its survival generated a powerful religious narrative. It was seen as divine intervention that God had protected his house. It fueled an incredible resurgence of faith in the aftermath.
But when structural engineers looked at it, what did they find? Was it a miracle, or was it just really well built?
Well, it was a product of brilliant, if unintentional, engineering. It was built by the Dutch in the 1880s with high-quality reinforced concrete and deep foundations. But the crucial feature was its design.
What about the design?
It has a relatively open ground floor with large arches. This allowed the massive surge of water to pass through the structure, dissipating the force, rather than building up and pushing against solid walls.
So the pressure never built to a breaking point.
Exactly. It's a perfect accidental case study in tsunami-resistant design.
And to illustrate the force that everything else was subjected to, we just need to look at the story of the PLTD Apung 1.
The generator ship. It's the definitive marker of the wave's power. This was a 2,600-ton ship, an electric generator anchored at sea.
And the tsunami just picked it up.
Picked it up and carried it 2 to 3 kilometers inland, depositing it on top of residential houses. It's still there today, a monument. It's the most visceral reminder you can imagine of the kinetic energy involved.
Moving west to Sri Lanka. Struck about 2 hours after the quake, over 35,000 fatalities. And there, the single deadliest event was the Paralaya train wreck.
The deadliest rail disaster in world history. Between 1,700 and 2,000 lives lost in a single event. It was just an appalling convergence of bad luck and fatal misjudgment.
Set the scene for us.
The train was the Samudra, the Queen of the Sea. It was packed, way over capacity with holiday travelers. It had been stopped near the coast because the initial quake had damaged the tracks ahead.
So it's a stationary target, just 200 meters from the sea.
And when the first, smaller wave hit, the passengers thought the heavy steel train was the safest place to be. Many stayed inside, others climbed onto the roof to get a better view.
A fatal mistake.
Because a second, much larger wave, maybe 6 or 7 meters high, struck moments later. It was so powerful it lifted the heavy carriages clean off the tracks, smashing them into the surrounding trees and trapping hundreds inside. A truly horrific scene.
Then we have Thailand. Over 8,200 deaths, a huge number of them foreign tourists, especially in places like Khao Lak.
Khao Lak was hit harder than nearby Phuket, mostly due to its coastal geography, which caused the waves to build higher and push further inland. And it's where we saw the devastating second wave trap.
Right. The idea that the danger is over after the first wave.
Precisely. A tsunami is a wave train, not a single event. Many people who survived the first wave returned to the beach to help others or check on belongings, thinking the worst was over. And then a second, often much larger wave arrived and caught them completely exposed.
The story of the Maria Bilan family from the film The Impossible really captures the sheer physical trauma of being caught in that.
It does. It's essential for understanding that it wasn't just about drowning. It was about being battered by debris in that black water, concrete, furniture, vehicles, while fighting a violent current. Survival was almost a matter of pure chance.
And finally, the Maldives. A completely different kind of impact.
Totally different. As a nation of low-lying coral atolls, they don't have a continental shelf for the wave to shoal on, so it didn't arrive as a towering, crashing wall.
It was a surge.
A massive, relentless, rapid surge that just flooded across the islands. The martial arts star Jet Li was there, and his account is perfect. He said the water just rose with terrifying speed. 2 steps, and it was at my hips, he said. 2 more, and it was at my chest.
The death toll was lower, but the economic damage was immense.
Devastating. The surge contaminated their freshwater aquifers with salt and wiped out the tourism infrastructure that their entire economy depends on.
All of these stories have a common thread, a tragic lack of awareness. But there were groups who knew exactly what was happening. Let's talk about the human element, the role of knowledge.
Yes, this is one of the most powerful parts of the story, the contrast between those who knew and those who didn't.
I'm talking about the Moken people, the Sea Gypsies.
They are the gold standard for indigenous knowledge as an effective defense. They're a semi-nomadic community living along the coasts of Thailand and Myanmar, and their culture is built around ancestral folklore.
They didn't need a supercomputer.
Not at all. They saw the ocean recede and instantly recognized it as the laboon, the wave that eats people. Their oral history, passed down for generations, was unequivocal. When the water disappears, you run to the highest ground and you do not come back.
And the result?
Entire Moken villages evacuated immediately. They suffered almost no casualties, despite being directly in the tsunami's path. Their ancient knowledge proved more effective than any modern technology that day.
It makes you wonder why that knowledge wasn't more widespread in the region.
That's a complex question. The Moken are a highly specialized maritime culture. For other, more settled communities, that specific folklore about rare seismic events can fade over centuries if it's not central to daily life. They become reliant on modern systems that, in this case, simply didn't exist.
We also heard anecdotal reports about animals, elephants fleeing uphill, that sort of thing. Is there any science behind that sixth sense?
The theory is not so much a sixth sense as it is superior physical senses. It's thought that some animals might be able to detect the P waves, the primary seismic waves that travel through the ground much faster than the tsunami travels through water.
So they get a few minutes head start?
Or they might hear the low-frequency infrasound from the rupture. It's a compelling idea, but the scientific connection remains unproven. It's not something we can build a reliable warning system around. Not yet, anyway.
So if ancestral folklore was one defense, the other was modern education, perfectly embodied in the story of one 10-year-old girl.
Tilly Smith. Her story is foundational to disaster education now. She was a British student on holiday with her family on Mai Khao Beach in Phuket.
Now, what did she see?
She saw the sea start to fizz and froth and then recede rapidly, and she recognized it immediately.
No.
Just 2 weeks earlier, in her geography class back in England, she had done a lesson on tectonics and tsunamis. She knew exactly what it was.
A 10-year-old girl.
She became hysterical, telling her parents, "There's going to be a tsunami." Her certainty convinced her parents, who then convinced hotel security to evacuate the beach.
And the result?
Mai Khao Beach recorded 0 fatalities. Tilly Smith is credited with saving around 100 lives. It is the single most powerful validation for integrating disaster education into school curricula everywhere.
An incredible story. Let's turn to the aftermath. The immediate humanitarian challenge must have been staggering.
In places like ACE, it was apocalyptic. They were racing to bury the dead to prevent a secondary disaster from diseases like cholera and typhoid. But the international aid response was so massive and so rapid that, thankfully, major outbreaks were averted.
And out of that chaos came one of the most surprising outcomes, the peace dividend in ACE.
A truly profound geopolitical side effect. For 29 years, the Free ACE movement, JAM, had been fighting a brutal independence war against the Indonesian military. The tsunami devastated both sides equally.
It forced them to cooperate.
It did. They had to work together just to get aid to survivors. And that forced cooperation built just enough trust to create a political opening. In August 2005, they signed a peace agreement that ended a 3-decade conflict. Lasting peace, born from shared catastrophe.
The reconstruction effort was massive. The mandate was to build back better.
The scale was biblical. They had to build 140,000 houses, 1,700 schools. The international community pledged over $7 billion in aid, but that massive influx of cash created its own problems.
Sudden inflation.
Dramatic inflation, yes. Aid agencies were competing for limited materials and labor, driving up prices. It also created social friction.
How so?
The quality of housing built by different NGOs was wildly uneven. You'd have one family in a high-quality brick house next to a family in a substandard timber one. It created jealousy and fragmented communities.
A lesson in the complexities of post-disaster aid.
A very hard lesson.
Okay, let's move to the most critical legacy. The evolution of warning systems. Because the 2004 tragedy happened, fundamentally, because the Indian Ocean was a technological blind spot.
A total vacuum. We had the Pacific Tsunami Warning Center, the PTWC, but the Indian Ocean had no unified system. It was deemed too rare an event to justify the investment.
So when the 9.1 quake hit, what happened at the PTWC in Hawaii?
They detected the earthquake immediately. Their seismometers are world-class. But they faced 2 fatal hurdles.
The first being the verification gap.
Exactly. They could see the massive quake, but they had no way to confirm if it had actually generated a tsunami. There were no dart buoys, no sea level sensors in the Indian Ocean.
They could see the trigger, but they couldn't see the bullet.
A perfect way to put it. And the second hurdle was the communication gap. Even if they had been 100% sure a wave was coming, they had no official protocol, no red phone to call authorities in the region. There was no one to warn.
A complete systemic failure.
Which led directly to the UN mandate to build the Indian Ocean Tsunami Warning System, the IOTWS.
And that system fixed the gaps.
It did. It was a monumental effort. A new network of seismometers, coastal sea level gauges, and most critically, those dart buoys deployed across the deep ocean.
The buoys that can actually measure the wave passing overhead.
Yes, a pressure sensor on the seafloor detects the change in the water column and sends a signal via a surface buoy and satellite. It provides conclusive proof that a wave has been generated.
But this new system created a new problem, the Cry Wolf Challenge.
The dilemma of maintaining public trust. The perfect example was in 2012. An 8.6 magnitude quake off Sumatra triggered the new system perfectly. A basin-wide alert went out, millions evacuated.
But the tsunami was negligible.
Almost non-existent. Because it was a strike-slip earthquake, the plates moved horizontally, not vertically. It displaced very little water. But imagine the impact. Massive, expensive evacuations for a false alarm. It creates evacuation fatigue.
People stop listening to the warnings.
Exactly. The system had to evolve again. It had to get smarter.
And this brings us to the cutting edge. Petaflop PS computing and AI. We're talking about India's Terang system.
Terang, which means wave, is the pinnacle of this technology. It's powered by a high-performance computer with 1 petaflop PS of processing capacity. That's a quadrillion calculations per second.
And that power solves the speed and the Cry Wolf problem.
It does. In 2004, analysis took hours. Terang can detect a quake, characterize it, and issue a fully validated and modeled alert in under 2 minutes.
Under 2 minutes. Is it simulating the tsunami in real time?
Yeah, even with the supercomputer, that's too slow.
Oh.
The AI uses a different approach. Scientists have pre-simulated thousands of possible tsunami scenarios, every size, location, and type of rupture.
So it's a massive database.
It's a 2-petabyte database. When a real quake happens, the AI doesn't calculate from scratch, it searches. It instantly matches the incoming data to the best fit pre-run scenario and uses that to forecast wave heights and arrival times with incredible speed and accuracy.
And they test this system constantly.
With massive drills like IOWAVE 25, simulating a 9.2 quake to test the entire chain of command, right down to the last mile, the warnings reaching the villages.
So wrapping this all up, the 2004 event showed us this terrifying geological power. shifting the planet's axis and exposing the fragility of our coastal lives.
And the monumental achievement since then has been the transition from that total silence to the 2-minute AI-driven alert capability of today. It's a colossal achievement in applied science and global cooperation.
But as you've said, technology is only part of the solution. The stories of the Moken people, the mosque, and especially Tilly Smith, they show that the ultimate line of defense isn't just hardware.
That is the final takeaway. Technology is the early warning, but social consciousness and education are the ultimate defense. The system can issue an alert in 2 minutes, but if people don't know what to do or don't believe it, those 2 minutes are meaningless.
The last mile of any warning system isn't a wire or a computer, but a human mind prepared for the unthinkable. So we'll leave you with this thought. If you were on a beach today and you saw the ocean suddenly recede, exposing the seabed, what would you do? Would you pause in curiosity or would you run for the highest ground you could find?